This submission had its roots in this little spark of inspiration that I had on a walk at the start of this year. What if? What if this could be a proof that the chromatic number of the plane is 7? Or 4 plus 3 proof? Hopelessly naive. I'm certain it is nowhere near so trivial, and yet this image stuck. Just a few months before Aubrey de Grey pushed the lower bounds for the Hadwiger-Nelson problem up to 5, I got interested in this problem. If you want to color every point in the plane without giving any 2 points at distance the same color, how many colors do you need? At least 5 as we know now, at most 7. This problem has lasted the better part of a century. And in this video, once again, I'm going to try and punch way above my weight, because we will in fact be building up to at least a sketch of a proof. This is by no means final nor peer-reviewed. To keep this video accessible and interesting not just to those in the know, but as many people as possible, the first chapter will be a simple graph coloring crash course. If you feel right at home with graph theory, feel free to skip right to chapter 2. In chapter 2 we will lay one of 2 important foundations to tackle the Hadwiger-Nelson problem. We're going to explore a strong lower bound for graph coloring and how we can use it in structured graphs to rule out entire swaths of coloring. In chapter 3 we will try to find optimal coloring rules for the Hadwiger-Nelson problem, and we're going to instantly run into a brick wall. And we're going right with the head through that wall. Once we are finally prepared, we are going to see if we can't actually break this problem down and give it a human comprehensible solution. There will be a lot of pretty geometry involved, and whereas previously I simply didn't manage to really tangle with finite graphs, here we are actually going to try to develop a deep understanding for both the finite and the infinite side to this problem, and how they are inextricably linked. Let me give you a quick rundown of graph coloring. Some set theory and a couple select other bits of math would be of help, but I'll try to visualize everything to foster quick understanding. Graphs have points we call vertices, often V and U. Vertices are connected with lines we call edges. We call these vertices adjacent. Vertices and edges make graphs. Enumerating vertices as Vn is also common. This is what the complete graph K3 with explicit sets looks like. Take note of this one, it's going to appear a lot and will be very important. In a complete graph KK, every vertex is adjacent to every other vertex. K3 is the largest complete graph we can embed in the plane, so K4 or higher won't make an appearance here. A graph coloring is a mapping of vertices in V to colors in C. A coloring is proper when no adjacent vertices share a color and all vertices are colored. This coloring is improper because of a coloring conflict. And this coloring is improper because not all vertices are colored. For this video, unless stated otherwise, a gray vertex isn't colored gray, but uncolored. Partial colorings, though improper, will be pretty important too. This here is a proper 3 coloring of K3, and it uses the least number of colors possible. Well, somewhat obviously. That brings us to the chromatic number of a graph. For K3, that's 3. We can invert the coloring function to get color classes, which gives us the set of all vertices having a certain color. Cycle graphs with n vertices are called Cn. Though not really important for this video, they will be useful in explaining some of our foundations. This here is C5. Odd cycles, as you can see, need 3 colors. Subgraphs and induced subgraphs in particular are really important too, and very often are called H. Subgraphs are only induced when they carry on all possible edges. Edgeless induced subgraphs are independent sets, and we call the largest such set alpha. Alpha is useful because we can understand it as a measure, and comparing it to the measure of the graph's vertices, we can derive a lower bound for the chromatic number of the graph, albeit a fairly imprecise one. And last but not least, the neighborhood of a vertex or a set of vertices are all the adjacent vertices. Now it's time to build towards some new stuff, slowly. When we color a graph, that creates logical constraints on vertex neighbors. If we give one vertex here color 1, blue, then the other vertex must have a different color. If we can get away with only 2 colors, then knowing that a vertex can't have color 1 means it must have color 2. Have a look at case 3 again. Limited color sets and exclusions can force deterministic color choices, and those will be pretty important. Let's talk about special neighborhoods, exclusion zones. I used this concept all the way when I first got into this problem, but I certainly did myself no favors by not defining clearly enough what they are and why I call them that. Exclusion zones are just neighborhoods, but they are only proper when they are neighborhoods of monochromatic sets. This will be crucial when we're gonna introduce a stricter way to understand coloring optimization. Now, we will need a measure for this chapter, and that will be the simple counting measure. Measure of v when our graph is k3, 3. Alright, it's finally time to get a little serious. We are highly interested not just in finished colorings, but in the process of coloring itself. How do we get from an uncolored graph to a properly colored one, and optimal at that? We are going to need 2 special measures. First, the colored vertices measure. This one is very simple really. How many vertices did we color? Let's color the 3 vertices and watch our progress. So far, so good. Now, the chromatic exclusion pressure is a bit more complicated. When we color one vertex in K3, we exclude 2 vertices from having that color. And with that, we can build a much tighter and general lower bound. Take note of what P is. 1 plus CEM divided by CVM. We colored one vertex and excluded 2. The chromatic pressure of our graph is now 3, and it will stay that way. Let's take a small detour. The pressure bound P under certain circumstances, which are optimal K colorings with balanced partitions, is nothing but an overly fancy independence bound. CVM will be K times alpha. In K3, K is 3 and alpha is simply 1. CEM then will be the measure of what each partition excludes, which inevitably will be all other partitions. So that's the measure of the entire graph minus one such partition, or alpha times K. And now we substitute. Factor out K. Cancel the 2 alpha terms in the dividend, and that's our independence bound. Let's talk about actually optimizing chromatic pressure and graph coloring in general, not just for slack integer values. Here we have C7, and again we color a single vertex. This time our choices matter. Let's color that vertex on the right. Something really important just happened here. See where we have 2 vertices colored but only 3 excluded? P has dropped to 2.5. We color another one, and it's yet a bit lower. But we're out of space for the first color, and we do all of that again. The top vertex is excluded by both colors, and so must get a third coloring. I want you to take note of how we optimized. Despite not being a bipartite graph, a graph we can split into two independent partitions, our coloring is strictly optimal when we treat as much of the cycle with only two colors as possible. We are inherently pressured to reuse colors we already admitted to and to delay use of new colors as much as we can. Let's see if we can do something with that. So we have a single vertex in the plane, counting measure 1. Its neighborhood is a circle. That would have a measure of 2 pi and then some length unit, here the arbitrary u. Yeah, this isn't going to work. Counting and Lebesgue measure don't mix, now do they? We're clearly not ready. So let's throw some shade at the Lebesgue measure. Don't get me wrong, it's a great measure and all, but as any measure it has things it is adequate for and things it is not adequate for. Let's look at intervals, open, mixed and closed. Counting none of the endpoints, 1 or both. The Lebesgue measure just collapses the measure of these intervals. Can we have that? No, we cannot, and that will become clearer and clearer as we go on. To get a bit more of an intuitive sense for this, consider the decimal numbers. To count from 0 to 10 and beyond, we need 10 numbers, but the 10 is not included. There is a general sense here that a partially bounded interval from 0 to x should have length x. And we do want a measure that does this and more. So here is a bold idea. We will make them mix. U is our stand-in for any sane length, so long as we use it consistently. Then the trans-dimensional measure is a Hahn series of measures with different dimensional grades. Okay, so that got a little weird and complicated quickly. Here, think of it as a bizarre polynomial that isn't a function. 2 square centimeters plus 3 centimeters plus 5. That is a trans-dimensional measure. That 5 probably feels off here, doesn't it? But our 0 term naturally looks like this. Anything to the power of 0 is 1, and that goes even for our units. So like this, we get a measure that does everything we need. We get full arithmetic. Remember, we need to divide arbitrary mixed measures. We can treat different dimensionalities simultaneously. And we also get full Lex ordering, meaning we can compare the size of different trans-dimensional measures. Now, we are doing a lot of simplifying here to avoid bringing in even more hard math from other fields. We could open a big can here, and we won't. And we'll simplify even further. The Hadwiger-Nelson problem is scale invariant. We don't really need explicit units at all. The pure dimensional grade is enough. Think of it like this. T is a unitless unit. T is the answer to the question of what the dimensional nature of a measure is. This will be weird and complicated enough. How do we measure these different intervals precisely? That matters quite a bit. Let's have a look at the open case first. If we measure like that, then the open interval is atomic. It has length t. That means that our other cases count the endpoints as a positive counting measure. Alternatively, we can also do a partial count. Now a partially bounded interval has measure t, which means that an open interval here has measure t minus 1. Oh yeah, that negative term is not an artifact. That'll get really important to you. Last, the closed case. I think that's clear. Let's see about tiling a number line. Think of it like trying to craft a measurable coloring for the 1D case of the Hadwiger-Nelson problem. Open intervals leave gaps. Closed intervals have overlaps and internal edges. Really not good. But if we have partially bounded intervals, now we're getting somewhere. Take at least one important lesson away from this. If we have edges between all points at distance 1, we explicitly need a mixed boundary to get a tile with maximum diameter. These single endpoints may be infinitesimal, but they are by no means irrelevant. Let's build just a little more intuition. Think of the polynomial t plus 2 and that squared. Hey, that's not just a square, that is a square with an exact count of the boundaries. 4 sides, 4 corners. These are n cubes. We're really not breaching into new frontiers here. Okay, what about this? t plus 1 squared. Now we have this partially bounded square. Let us... well, look at that. They tile the plane perfectly. No overlaps or gaps. Yes, this applies to n-cubes in general too. See how there are lots of indicators that mixed boundaries are very natural and useful to us? So to future-proof we will treat them as atomic, despite some fun complications that come with that. Okay, let's bring our previous framework back. A vertex and its exclusion zone. That doesn't look good, and frankly do consider this a threat. 2 pi t is very much infinite, and 1 plus 2 pi t is more than a little bigger than 7. We have an intense need for optimization here, but we already know that it's possible to optimize at least down to a nice and finite 7. Let's place another vertex nearby. See those intersections? Yeah, we don't count them twice here either. That means we subtract 2. We actually got a better ratio. Infinitesimally so, but there is also infinite space to optimize. Let's build one last piece of intuition, comprehend one important lesson, and then we can actually tackle the big problem. Those finite negative terms, they give us Jordan-Brouwer separation. If that doesn't ring a bell, think of it simply as having shapes with a clear inside and outside. Here we have a circle and a vertex with their respective exclusion zones. See how that circle excludes an annulus and that smaller circle is fully inside it? This is what CEM optimization for the Hadwiger-Nelson problem looks like. If we have a monochromatic boundary, encased vertices are free. Think of the cost of that vertex. It is 2 pi t minus 2 pi t. 0. Once you move the vertex outside, it costs something. A big issue with the Hadwiger-Nelson problem is the looming threat of unmeasurable pathological colorings, fine specklings of color. But this makes very tangible predictions for our problem. Not just can we use measurable colors, we in fact must. Pathological colorings are at best irrelevant in some parts of the overall graph and are at worst actively detrimental. To further optimize, we make maximally large tiles and let the exclusion zones of those tiles overlap. That sounds an awful lot like the only good proper colorings we know. Back to the Hadwiger-Nelson problem, and this time for real. This here is where it's going. 7 colors. But we can't just assert that this is it because it looks a little pretty. So what we will do is look at and analyze induced subgraphs of the plane, and we are going to build this up color by color. The first color is trivial, of course, but note how the boundary looks. For the sake of convenience, these disks are the biggest monochromatic shapes you can get in the plane. There isn't even so much as a single vertex to discuss. 2 colors. This is still trivial to prove, but very much important to look at closely. Let's uncolor our disks and then color a single vertex back. This vertex will now exclude an arc in the other disk. Remember, we are not looking at the whole plane, but just these 2 disks, and we already know that 2 colors suffice. 2 colors, can't use one, must use the other. That arc excludes an area in the first disk, and there is the bipartite coloring collapse. It will return pretty soon. 3 colors. All the way back in the polymath project, I may have claimed that this graph too is totally immune to pathologies. I was not able to rigorously show it, but when we look at these 2 exclusion zones overlapping, we get a pretty natural sense it should be that way, right? It is. But let's take that third disk back for a moment and just consider an arbitrary vertex that excludes both of our still considered disks. Our pressure bound is 2 plus some infinitesimal term, and that still rounds up to 3. But if you take all 3 disks and miscolor a vertex, that same infinitesimal carries us over 3 to needing 4 colors. Forget about a pathological freaky coloring, we can't even have a discussion about maybe having 1 deviant vertex. And here is where we would put a proper finite proof of that. If I had one. I do in fact, but it's a little too involved for this video, for now. It deserves its own video. Besides, with the tiniest adjustment, I actually have a much easier and more relevant proof. If you want to challenge yourself, this would be the moment. See how soon you can predict how we are going to prove that even with 3 colors, measurability is not optional. Let me show you the well-known Moser spindle, and my spin on it. See this rhombus? It's a K3 graph that has been extended, and now the far vertices must share a color if we have only 3 colors. You could say they are connected by a sort of anti-edge. Let's put down another rhombus like this. Now the 2 vertices at the bottom are at unit distance, so they share an edge. But anti-edges are transitive, so they share an anti-edge too. So they must share a color and mustn't share a color. That's a contradiction. A contradiction to what? 3 colorability. Alright, here is the proof. Take just one more vertex so that we can place a rhombus like that. And sweep. That arc there is the quick depth for pathological colorings. Let's have a look at that arc's exclusion now. Do you see the problem? We know there are only 3 colors we need here. So, where we exclude the other 2 disks, we can only have 2 colors. And we know what happens there. The bipartite collapse. Okay, so far so good. Do we just add that 4th disk and somehow it can only have the 4th color like you saw in the complete construction? Yeah, nah. Here, check out the blue exclusion now. We only exclude the lens of that new disk, not the whole thing. We can, and for the sake of optimization, in fact, must color the complement blue. Let's bring the rhombus back. See that? Edge and anti-edge when we try to state 4 colors, but only in that lens, or on a lens on the opposite side. This is our exclusion down. Note that it does not exclude all of the 2 nearby disks. Alright, we need more. Zoom out 2 more disks. Let's just recolor these other 2 areas for now. Is this optimal? Well, let's check out the combined exclusion zone of our 3 lenses. Look at that. The 3 center disks are now fully excluded. Those tiny islands you see, they're useless for optimization. Remember that these are encased vertices. They are free if and only if they adopt the color of their surroundings. Now we have something pathological going on. These outer complements are no longer forced into the opposite color. They have actually become color agnostic. They will either accept the 4th color or the one opposite. And that's actually it. See, in this large periodic tiling, for each pyramid, the center 3 are forced to be monochromatic, which is only everywhere. Now, take note of the fact that these 4 colors dominate. We've gotten everything we will for this graph. Every vertex in the whole plane is either excluded by one of these colors or colored by it. Okay, we're close to the finale. The gaps are all that is left. We have front-loaded all of our gains and this will show now. Here, let me bring in one of these colors. We will always have 2 of these close, no matter how we try to shuffle the colors around. And this is the combined exclusion zone. Let this marinate for a bit. If we were trying to dodge a 7th or even 6th color, what would we have to do? We can't expand the original 4 colors, but there are vertices there that must be colored. We can only do one thing. We need to shuffle the 5th color around to somehow get one of the colors, one of the other 4 colors to stop excluding the other gaps which are all at that devastating unit distance. But the fifth color can't even expand into the big disks above or below. Remember again, encased vertices are free only for the surrounding colors. So all we could do is expand the color into the other two nearby areas. Now, if you remember what we saw about the overlapping exclusion zones of the large colors, each gap disk is excluded fully or partially by 3 disks of a given color. Maybe go back and look at it for a little bit longer. But as we see in this pattern here, we don't have access to all 3 big disks of a given color. This is never the case. Not while still holding the fort and the gaps, so to say. And so, once we add another set of gap disks, we need that 6th color, inevitably. And here is the anticlimax, ironically. If all of this so far actually holds, then the proof for the last color, quite ironically, is the most trivial one of them all. The 5th color didn't have access to 3 disks of a given color anywhere to even make an attempt to free up the last gaps. The 6th color is in the exact same boat. And that's it. 4 plus 3 colors. 7. Again, this is just a sketch of a proof, not peer-reviewed material, this is just hobby work. And pressed out under time pressure too. I hope you enjoyed the video and maybe I'll soon upload some more. There is a lot more here to explore and I had a lot of things to skim over.